Hello and welcome to another Advent of Code Day. Today we're doing day 9 and let's jump into it. Okay, so for day 9, our input is a series of numbers, and I got really confused when reading the problem description, so I simpled it down a little bit here. But basically we have a bunch of inputs here, and we're supposed to be looking for a number which doesn't match a particular constraint, at least for part 1. I'm going to call that the weird number here. I don't remember what they referred to it as in the problem. But basically, every number before that number within a fixed size window. So in the example problem, the fixed size window is 5 numbers. So you would imagine a segment of numbers like this. And inside that segment, at least 2 of the numbers added as pairs should equal the next number. So this next number, 55, for example, 40 plus 15 is going to equal 55. So this is not a weird number. And you're supposed to search for the first weird number in this range. In the sample problem that they give you, the window size is 5, but in the actual input, it's 25, and we'll actually have to adjust our function for that when we get there. But I got super tripped up on the 5 versus 25 thing, but hopefully you won't now that I've explained it. But anyway, we're actually going to reuse some of the code that we wrote in part 1, or write code that's very similar to the code we wrote in day 1 for computing a two-sum, which is what this pairwise addition is called. And that's part 1. For part 2, we're supposed to find a contiguous chunk of numbers which add up to the weird number. And I'll show you kind of the brute force approach to solving that, as well as a smarter solution. But anyway, let's do the parsing. Parsing is actually really easy today because it's just parsing numbers. And so we can just do return int line for line in s.splitlines. And again, this should look familiar if you've watched any of the other videos. Python 3 parsing. S is not defined. Wait, what? Oh, input s. Yeah, there we go. My example code was broken. But anyways, it's just parsing these into integers. Pretty straightforward. So with that out of the way, let's move on to part 1. Okay, so this one, I actually thought part 1 was more difficult than part 2. And it definitely is from like an algorithmic perspective. But let's do part 1. So we have to have a window size here. So note that usually my compute function has no parameters, or it's just the input. But here we have a separate n, and we're actually going to pass a different n whether we're doing the sample input or the real input. So in this case, I've passed n equals 5 here. I've also made it a keyword only argument just so it, reads a little bit better down here instead of just a 5 that's hard to explain what's going on. Okay, so the way that I approach this problem is I want to build up that special preamble list. So like these 5 numbers here. And so I know that I have to start before that, after that. So the first number that we could ever look at is at index 5, because this is 0, 1, 2, 3, 4, and 5. So that gives us a starting point for the numbers we're looking at. So let's write that loop for I in range. And often when you write range len in Python, you're probably doing something wrong, but in this case, I can't really think of a better way to write this. Although my actual solution just used enumerate, so I guess I can't think of a better way. Okay, but we have a range. This is going to give us, if we just run this right now, that's just going to give us the integers from 5 to the length of the list. rs1.py, you can see, incrementing numbers here, and then none. Oh, because compute returns none. I was like, wait, where'd the none come from? And we want to look at the values before that. So we want to grab out a slice from all of those values. So we're going to do previous equals input n, I minus n to n. Is that right? This is not how I did it, but let's see. So, no, this is not the right answer because we get this I minus n to, oh, not to n, to I. There we go. Okay, so now we always have 5 numbers, and they are the 5 previous numbers. And so we can look for the property inside these numbers here. So basically 2 of them should add up to 1. I'm going to use the iter tool solution just because it's the shortest code. iter tools. We actually showed in day one, which I will link day one's video. I think it was day one. Was it day one? Let's see, day one, part one. Yeah, it was day one. So I'll link day one's problem below so that you can look at that as well. But anyway, these are our previous, and for x, y in itertools.combinations, previous 2. So we're looking at 2 sum here. If x plus y is equal to input I, this is the successful case, and so we can break out earlier. I'm going to use a little trick here with for else. I have a video on for else, so I'll link that as well. But basically, if break happens here, the else block will not run. But if else does run, then we know that we've never satisfied this condition here, and so we've found a weird number. And so then we can just do return input of I. And if we run this now, we should see our weird number, which is 127. And that is actually, I forgot to put that down here. That is the number that we expect for part 1. And so if we look at this here, 127, the previous 5 numbers, no combination of these will add up to 127. So that's definitely our problem number. So that's part 1. The only real improvement that I could do here is this is slightly slower than it needs to be. Now granted, this itertools combination is n squared, but it's over a subset of our list. And so it doesn't actually dominate the overall runtime here. So if we do our runtime analysis here, this is O of n minus 5 or something like that, and the constants go away in ON notation, so this is just ON. This slice is actually a little bit expensive. You could avoid this by using a an iterative slice instead of a copy slice, because this makes a copy of a chunk of your data. But overall, this is a constant multiplier on ON, so this is still a constant time thing, which also makes this a constant time thing. Now the constant is based on this little n here, and so when we do constant of 25, these are actually kind of slow, but overall it doesn't impact the runtime, and so the runtime is overall ON. But yeah, let's go on to part 2 now. So we actually need this weird number for part 2, because part 2 is find, oh, I already put it down here, perfect. Find a contiguous chunk. Let me put up the parse. Oh, we don't need the parse because we got here. Find a contiguous chunk which adds up to this number. Now, if you've done a lot of software interviewing, this should ring a bell for a particular algorithm. I'm going to show you that algorithm in a second, but first I'm just going to show you the, the brain dead brute force solution. And fortunately, the input is small enough here that the brute force solution does work, and it does. It works for the large problem as well. But a lot of the advent of code problems will have solutions where brute force takes a prohibitively expensive amount of time, and so you can't actually complete it within your lifetime. But let's do compute brute force, and that's the first one we're going to do. So for our brute force solution, I'm just going to try every single possible sum of this list and see if any of them satisfy this number. And so I'm just going to write some for loops here, which will generate all of those combinations. The first for loop is for I in range len input. And again, like in Python, if you're doing range len input, you're often doing something wrong. There's usually better ways to iterate through a loop in Python, but in this case, it kind of makes sense here. And then we want, so this is going to be the beginning of our range. We also want something that's the end of our range. And so we'll do for j in range I plus 1 to len of input. That'll give us our range here. So range, or r equals input I to j plus 1. Note that we're using j plus 1 here because we need to include the end value. Whereas, if we just did I to j, we would have an empty list for the first one because the end of a slice is non-inclusive. And then our condition is just if sum of r is equal to prev number, then the problem wanted us, what did the problem want us to do? It's like minimum and maximum. This actually tripped me up too. So minimum value and maximum value. When I read the problem, I initially thought this was like first value and last value, but no, it is the minimum value of this range here. So we can do return min r plus max r. And again, if we don't hit that condition somehow, raise assertion error unreachable. And so if we run this, it should work. Python 3 part2.py. And we do get 62. This is the number that we expect. I'll show you the range for that. It's actually right here. Yeah, it's this range here. So 40 plus 80 plus 47 is 127. And so the minimum value is 15 plus 67 is 62. I should have put that down here. Expected 62. Okay, so this is the brute force solution. Let me show you the algorithmic efficiency here. This is ON, and this is ON. And then this is, also ON, because it has to do a copy that may be at most the length of the list. And so overall, this is going to be n cubed. And I'm going to show you a solution that we can actually do in linear time, which is pretty neat. And the name of the algorithm that we're going to implement is called sliding window, which is actually kind of like a meme in like interviewing leak code sort of deal. Like, oh, all I can think of is sliding window. My life is a lie now. But anyway, the idea behind sliding window, and I've actually drawn a little diagram here with the sample data here. The idea behind sliding window is to only maintain three things: a beginning, an end, and a sum, and walk along the list as you need to either increase or decrease your contiguous sum. So if we look at our starting state here, our beginning and end are both pointing at this first number, and our sum starts as the initial value. So here it is 35. And you'll note here that 35 is much smaller than our target. So then we're going to move the end value. We add the new value to the sum, and then we repeat that operation. So since we move the blue one to the 20 down here, now the sum is 55. It is still too small, so we're going to continue to move the end until it's not too small. And I skipped a few steps here because you can imagine, moving it to here, add 15, moving it to here, add 25, moving it to here, add 47. But when you get to that state, you have a sum that's 142. And in that case, the sum is now too big. So you start moving the start instead, and then you subtract the number out. So you subtract out 35 here, and then you have your new sum. And you keep moving those until you get to the point where you have a matching thing that maps out to your sum. And in that case, the start points at 15 and the end points at 40, and you get a sum of those internal values of 127. Now note that you don't have to do any of the internal summing here. You're really only just subtracting one number at a time. So it's much more efficient, both on space and on runtime. But let's implement this algorithm. The way I did this is I had a infinite loop, just because I knew that we should eventually get to a case where we match something. And we have three values here. We have start equals 0, we have end equals 0, and we have total equals input of 0. And so these are kind of those three variables that we had at this position right here. And we basically have three conditions here. So if total is less than our target value, then what we want to do is we want to increment the end and add that to our total. So end plus equals 1 and total plus equals input of end. And we have another case here. Elif total is greater than previous number. So in this case, this is this case here where the sum is too big and we want to move the right one over. So we want to do start plus equals 1. And, well, actually, let's actually subtract first. So total minus equals input start, and then start plus equals 1. So that'll remove the value and move start over. And then our last condition is when it's equal. So that's, it's not greater than, it's not less than, so it must be equal. And so we get to our case where we have, the right start and the end value. We can again construct this range and do basically this same code here. So if we do this, instead of I and j, we have start and we have end. This is actually no longer O1 since it's, or ON, because it's, a much smaller than n here. And so we can construct our range and figure out the min and the max between it. Is it n plus 1? Yeah, because it's 0 to 0 plus 1. Yep. So, and we actually don't need to do this condition here. We can just say min and max there, and we get our answer there. So if we do that with print compute sliding window, we should also get 62 twice, and we do indeed, which is pretty cool. The neat thing is part 2 doesn't actually depend on the window width. There's no n here, so I removed that parameter in my compute functions. But yeah, this is how you would implement a sliding window. Let's talk about the runtime here. It's actually kind of tricky to see the runtime, but you can think about it in your head that at most you would have to do twice as many loops through this loop because you only move one of start and end at the same time. So if you were to move each of them one at a time all the way to the end of the list, you would move it 2 times n times. But again, constant factors on on just make it on. So this is overall on, and the space overhead is constant. There's actually no additional space here. I do construct some additional space here, but you can compute min and max without making a slice here. So you can do this with no space overhead. Worst case, this is linear space overhead the way I've written it, but you can do it without that. So, so this is, well, overall on time and O1 space, assuming I fixed the slice. But anyway, that's day 9. Hopefully this was helpful. I will see you around for day 10. Thank you for watching. See you in the next one.